Welcome to the presentation of our paper, Designing for Human Operations on the Moon, Challenges and Opportunities of Navigational HUD Interfaces. This work represents a collaborative effort among the German Aerospace Center, the European Space Agency, and universities across Europe. The primary focus of this research is to explore the design of heads-up displays, or HUDs, for future lunar extravehicular activities, or EVAs, commonly also known as spacewalks. To this end, we've employed virtual reality to interactively simulate relevant mission scenarios, and we've evaluated these with experts. This approach has allowed us to elaborate on the key challenges that future astronauts might encounter in this unique environment, along with potential solutions to enhance their navigation and efficiency. Based on our research, we've then formulated design guidelines for HUD interfaces tailored to support future EVAs on the Moon. Finally, we propose enhancements for virtual reality simulations, aiming to improve their utility as an effective testbed. During the Apollo lunar landings of the 1960s and 70s, astronauts embarking on EVAs faced a wide spectrum of challenges. The lunar terrain, marked by a general lack of landmarks, combined with blinding sunlight and pitch-black shadows, made spatial orientation difficult. This challenge was further exacerbated by the cumbersome spacesuits worn by the astronauts, which restricted their visibility and mobility. Conducting missions in this unfamiliar and demanding environment, therefore, imposed significant mental and physical strain, often leading to reduced situational awareness and frequent navigational difficulties. Confronted with such obstacles, astronauts had to rely on relatively rudimentary tools, such as wrist-mounted watches, a sun compass, and analog maps. At times, these tools proved inadequate. Notably, during an EVA undertaken by the Apollo 14 crew, the astronauts struggled to pinpoint their location accurately, which forced them to terminate the mission prematurely. Fueled by a surging interest in lunar exploration, the ongoing Artemis program is on a mission to return human crews to the Moon's surface before this decade ends. This time, the spotlight is on the Moon's south pole, a region where vast reserves of water ice rest within perpetually shaded craters. Focusing on this geographic area is expected to amplify existing challenges and introduce new complexities, including prolonged communication delays and periods of radio blackout. To succeed in this ambitious endeavor, a new generation of astronaut-supportive technologies must be meticulously designed. These technologies are essential to ensure the safety and efficacy of human operations on the Moon. Our work explores the potential use of HUDs as a solution to these challenges. HUDs encompass a wide range of interfaces designed to overlay a user's field of view with pertinent data or even project 3D spatial information into the surrounding environment. Their key advantage lies in eliminating the need for users to divert their gaze from their primary tasks, thus enhancing work efficiency and reducing visual distractions. Indeed, the use of HUDs has already proven beneficial in various sectors. In the military domain, HUDs are, for instance, utilized to display navigational cues such as a compass in the field of view of the soldiers. This integration of digital overlays with the physical environment allows soldiers to remain aware of their bearings and objectives without losing focus on their surroundings. Also, aircraft pilots frequently utilize HUDs that project critical flight information directly into their line of sight. This includes real-time data such as altitude, airspeed, heading, horizon line, and even sophisticated navigational aids for takeoff and landings. Such technology not only enhances the pilot's perception of the environment, but also significantly improves situational awareness, enabling more precise and safer decision-making under the high-stress conditions of flight. In the automotive sector, HUDs are used to project vital information, such as speed, navigation directions, and safety warnings directly onto the windshield. This innovation allows drivers to keep their eyes on the road ahead, while simultaneously receiving important updates, significantly reducing the risk of distractions and improving reaction times to road conditions and traffic signals. However, as we look to the moon, the usefulness of HUD technology for navigation remains largely unexplored. This lack of empirical research is primarily due to the difficulty of replicating the lunar environment for testing. Traditional analog testbeds, which simulate some of the challenges associated with lunar navigation, such as extreme lighting conditions or reduced gravity, are slow to set up, costly, and logistically complex. Our answer? Virtual testbeds. These recreate lunar conditions in VR, capturing everything from the unique play of light and shadows to the specifics of lunar terrain and equipment. This virtual approach offers a flexible and cost-effective route to explore HUD applications for lunar exploration. Drawing on topographic scans of the lunar surface, we digitally recreated 64 square kilometers of the lunar South Pole, the likely landing site of the next human expedition. We took great care to maximize the realism of the environment, such as by accurately recreating the lunar lighting conditions. For an immersive experience, we utilized the HTC Vive Pro 2 head-mounted display. Specifically, based on existing literature, we identified 3 representative types of HUD solutions. Wearable HUDs offer users a digital overlay of contextually relevant information to enhance their orientation and task performance. Our prototype was based around a mini-map that provides real-time visualization of the user's location and surroundings. Spatial HUDs go a step further by projecting 3-dimensional content into the user's view of the real environment. This approach helps declutter the HUD, reducing the user's cognitive load. Our prototype focused on an augmented reality pathway, guiding users to their destination. Global orientation. HUDs expand the user's perspective beyond immediate surroundings, offering a big picture view, critical for strategic awareness in complex operations, such as by visualizing the overall mission plan. Our prototype displayed the cardinal directions and other key points of interest. Finally, as a baseline, we also included a non-HUD interface in the form of a wrist-mounted tablet. This interface offered a usability experience closer to the traditional maps used by the Apollo astronauts, allowing us to compare HUD solutions to more conventional navigational tools. 25 domain experts were recruited for the study, including 2 astronauts with previous EVA experience. Experienced engineers, instructors, and scientists were likewise taking part in the study. Our procedure began by letting the participants draw their imagined ideal version of a HUD for lunar EVAs, warming them up for the main task. Next, they navigated a 500-meter traverse on the moon in the VR testbed, with 4 distinct navigation features tested after each other. We employed counterbalancing to avoid order effects and utilized the NASA TLX to assess workload, the system usability scale for usability, and a presence questionnaire to gauge the sense of being in the virtual environment. We measured performance with metrics like route deviation and completion times, alongside semi-structured interviews to gather qualitative insights during both tasks. Our participants unanimously agreed HUDs have the potential to play an important role during future lunar operations, praising their ability to deliver essential information directly within the user's field of view, while leaving their hands free for other tasks. The use of tablets, on the other hand, was deemed cumbersome and potentially hazardous during EVAs. Several useful HUD contents were identified. Vital signs such as oxygen levels, heart rate, and suit temperature were deemed crucial for informing astronauts' navigation decisions. Maps displaying real-time information about lighting conditions, elevation, and other terrain features were likewise seen as important. It was, however, seen as crucial for this content to be displayed in an unobtrusive and context-sensitive manner. For example, astronauts should always maintain a clear view of their immediate surroundings while walking around. Participants also highlighted the importance of being able to control one's HUD. Machine learning adaptation and remote control from mission control centers were brought up as possible solutions. Most participants, however, agreed that astronauts themselves should retain direct control over their HUDs, referencing the need for astronaut autonomy within mission architectures. These findings were also supported by our quantitative findings about workload, system usability, and performance indicators, such as speed and traverse deviation, where the results indicated that especially HUD navigation cues are indeed preferable over heads-down solutions, such as the tablet. Overall, we could summarize our findings in the following design recommendations. Future HUDs should incorporate spatial conformal cues. Here, for instance, augmented reality markers such as waypoints placed in the environment likely improve terrain navigation. 2D conformal cues should be furthermore utilized to highlight safety threats. Importantly, existing color standards are vital for astronaut safety. Here, for instance, the existing color standards of the International Space Station should be respected. To avoid information overload and to prevent attentional tunneling, HUDs should offload non-essential info to auxiliary displays and design layouts that position crucial data against the uncluttered lunar sky, keeping the astronaut's view primarily clear so that the ground is visible at all times. The HUD should offer situational guidance, ensuring astronauts maintain control over their navigation paths. This includes the integration of both local and global orientation tools, providing astronauts with comprehensive information about their immediate surroundings and broader environmental context, like mini-maps and waypoints. Furthermore, the HUDs must be explainable. Navigational instructions should be clear and justified at all times. Lastly, we advocate for the integration of multiple interaction modalities within HUDs. Here, for instance, voice commands could be combined with buttons or gesture-based interactions. Therefore, we can create a responsive system that adapts to various operational scenarios, thereby offering astronauts a flexible and efficient means to access HUD functionalities. Also, if their hands are, for instance, occupied during a traverse. Our study could overall demonstrate that AR HUD technology could likely significantly ease the navigational burdens of lunar EVA challenges, such as poor lighting conditions. Our research highlights how global navigational cues and spatial AR could enhance performance, reduce workload for astronauts during future EVAs. Moreover, we've established virtual test beds as effective tools for examining EVA navigation scenarios, providing valuable insights for future interface designs in space systems. In future work, we plan the integration of passive haptic feedback, like mock astronaut gloves, to better emulate manual operations. Moreover, exploring full-body constraints through advanced motion tracking to mimic the actual movement in a spacesuit could be an interesting area of future research to enhance the realism of the simulation. We also plan to combine gravity offload systems with VR to mirror lunar locomotion. Furthermore, real-world testing during analog campaigns of HUD solutions, incorporating relevant physical constraints to the ground, would enhance the realism of the test bed. Lastly, investigating auditory cues to balance the sensory input, utilizing 3D audio to aid navigation, especially in high workload scenarios, could be a promising avenue of research. By advancing these areas, we not only refine our methods, but also enrich the insights into human-centric design for lunar exploration.